Okay, welcome back Physics 30s to our next lesson in Chapter 7. This is 7.5, and today we're going to be talking about the energy of decay. Okay, so to start, let's just quickly recap the types of decay we saw from the previous lessons. I'm going to put over here that we begin with a parent nucleus, and we'll look into all the different products that we can get. The first one is alpha decay, where we get a daughter nucleus and an alpha particle. Remember that an alpha particle is 2 protons and 2 neutrons. It's the same as a helium nucleus. Then we have 2 types of beta decay. Here we get another daughter nucleus, but we have 2 things be ejected in this example. We have a positive beta particle, or a positron, and a neutrino. We can have another type of beta decay that has a negative beta particle, or an electron, and it emits an antineutrino. And then the last type we looked at was where this is emitting energy in the form of a photon, and this is a high energy photon called a gamma ray, and so this is gamma decay. And what we're going to look at today is how much energy gets released when we go from this parent nucleus to its products or undergo these decay. How we'll measure the energy is look at the change in mass from what we have at the start to what we have at the end. Our example is going to be looking at alpha decay, where we look at the mass of the parent nucleus compared to the daughter plus the alpha particle. This would be similar for beta and gamma decay, but there's not as much mass for these beta particles, neutrinos, or the gamma ray. You would still have a mass defect from the parent nucleus to the daughter nucleus, but our example would just be for alpha decay. After we cover that calculation, we're going to look at what would happen if you were in the vicinity of a decay and got hit with any of these particles, and what's dangerous about radiation. So let's start with looking at the energy released by an alpha decay. So this is similar to the diagram on the previous slide. Let's use an example of uranium-238. So I've written the nuclear notation down here. Uranium-238, uranium has 92 protons. So if that decays to an alpha particle and a daughter nucleus, we know an alpha particle is 2 protons and 2 neutrons, so 4 nucleons, 2 protons. So we just have to figure what we have left here. If we had 38 and the helium nucleus has 4, there must be 234 here. And if we had 92 here and there's 2 here, it must be 90. So we can get those numbers just by subtraction. We look up that 90 protons is thorium, and we know what our daughter nucleus is, thorium-234. Now, to determine the energy that's going to be released, we're going to use a process similar to when we looked at binding energy. We're going to compare the mass of the uranium at the start to the thorium and the alpha particle at the end. Make sure you don't forget to include the alpha particle in these questions. So first, the weight of uranium-238 in atomic mass units is 238.0508. And the mass of thorium-234, 0436, and the helium, 4.0026, and these are in atomic mass units. So I have my total at the start. Next, let's find the total at the end. So I've just added those 2 together, and then I'll take my final mass and subtract that from the initial mass that we had. Do that subtraction, and I get an answer of negative 0.0046 atomic mass units. So if that much mass was lost, we now just want to turn that into energy. So first, let's turn these atomic mass units into kilograms. So we'll times by 1.66 times 10 to the negative 27 kilograms. And again, an answer of 7.636 times 10 to the negative 30 kilograms. Again, it's not a huge change in mass, but it is significant because we'll turn that into energy now. Using E is equal to mc squared, plug that m in for mass, and I get a number of 6.87 times 10 to the negative 13 joules, which may seem small, but that's for just one nucleus, and nucleus are really, really small. So it's a fair amount of energy. We convert it into electron volts, and we get 4.3 mega electron volts for just one of these decays. So if we had a lot of uranium nuclei decaying, we're getting a lot of energy. Lots of energy comes from changes in the nucleus. And we'll see that even more looking at fission and fusion in the next lesson. And for the next part of the lesson, we're going to consider the dangers of radioactive material and the dangers of their products. So first, let's look at an alpha particle. An alpha particle is ionizing, and ionizing isn't good because it knocks electrons off of your atoms and can cause changes in your DNA. So if it's ionizing, it can be quite harmful for us. Now, an alpha particle is ionizing. It has enough energy to knock off electrons. However, fortunately, it doesn't penetrate our skin. It can't even really pass through paper or aluminum. It doesn't take too much to block alpha particles, which is kind of good. However, if we were to ingest or inhale anything that was decaying or undergoing alpha decay, that would be a problem, as it could then cause some damage to us internally. The next two we're going to look at are beta particles. We have the beta particle plus the positron or the electron. This is also ionizing. Electrons can knock other electrons. We saw that in previous units. And these can penetrate the body a bit further. They're quite a bit smaller than an alpha particle. They can penetrate up to about 1 centimeter. So they're considered to be more dangerous than an alpha particle if it is outside of our body. You might be wondering about neutrinos, as these are really small, high energy particles. However, they are non-charged and again, really small. They're considered to be non-ionizing, and they pass through nearly everything. They're just going to move through pretty much the empty space of atoms because they're so incredibly small and not charged. So we don't have to worry about being damaged by neutrinos too much. And the last one is a gamma ray, and this is ionizing. This is high energy photon. Any EMR from UV and smaller wavelengths is going to be ionizing, and gamma rays are the smallest wavelength or highest frequency, so those can cause damage to our bodies as well. So all of those but the neutrinos were ionizing. So what's the danger of ionizing radiation? As I mentioned, it has the energy to knock off electrons, and this can cause damage to our DNA. So I'm going to start by showing a gamma ray here coming in and damaging a section of our DNA. Now this can be repaired, but if we have damage that is not repaired, it can lead to mutations and cancer. This can also happen with particles. So I just have an alpha particle here knocking off a different part of DNA. So just in the notes, it knocks off electrons and can cause damage to our DNA. So this isn't representing the electrons being knocked off, it's just representing damage to the DNA. The DNA can be repaired, but in acute exposures, high acute exposures, this means a lot of radiation in a short amount of time. You can have significant damage that may not be able to be repaired, a mutation, or even the death of cells. So we want to avoid exposure to high amounts. Now, you will be exposed to some radiation all the time. There's always little sources that we can't avoid 100%, and long-term low-dose exposure can lead to these mutations as well, which can cause cancer. So we don't want a lot of radiation, but there's some that we can't avoid. Let's look at some places that you might get exposed to radiation. So common exposure to harmful radiation. First one I'm going to put up is radio waves, because this is actually not exposure to harmful radiation. I think sometimes it's thought that because there's radio waves going around a lot that this will be harmful to us, maybe causing cancer. But radio waves are so low energy, they are not ionizing, and so they do not fit into this ionizing harmful radiation. Okay, so that's not what we're going to be talking about. Sources of ionizing radiation would be from radon gas, cosmic rays coming from space, yourself, you'll have a little bit of carbon-14 that is decaying in you, X-rays, UV rays, and a whole bunch of other places. Now, I put on some here like cosmic rays and yourself, that, well, you can't really do anything about, and they're not going to be really high amounts. Even X-rays, you don't get that many X-rays in your life. Hopefully you're not undergoing too many injuries. This won't be a huge contribution to the radiation that you're going to get. The most significant sources here are radon gas and UV rays. Radon gas is a gas that can leak into basements. It comes up from the ground, and it undergoes alpha decay. And you might be thinking, well, that's fine, it won't go through my skin. However, it's a gas, and so if it's in your house, you don't want to be inhaling it and having that damage you internally. For UV rays, this is coming from the sun. The sun sends a lot of UV radiation, which is ionizing and can cause skin cancer. Now, a lot of skin cancers can be removed. You can just get it cut off. However, some of them can be lethal or can be deadly. For an example, this is malignant melanoma, which can spread and unfortunately can cause death. So we want to avoid sunburns and getting hit with UV radiation so that we don't develop skin cancer. So this is an example of a sunburn. You want to avoid those as they increase your chance of skin cancer and malignant melanoma. So we want to avoid that. One way that we can do that is with sunscreen. So applying sunscreen, regardless of your skin color. I mean, people with more fair skin are more at risk to skin cancer, but all types of skin colors do have the potential for skin damage. So always good to wear some sunscreen or to cover up with hats, sunglasses, and clothing. And that's it for the video. So thank you so much for watching. I hope that helped you to understand the energy of decay, and I will see you in the next lesson.